Robotic Lower Limb Prosthesis by Kathy C., Anthony Chalka, Dennis Cruz, and Hudson Tete. The professor was Professor Howe, and our mentors were Bowen and Chun Hai. The problem we wanted to address was over 158,000 amputations occur each year in America, and about only 2.2% of the amputations occur at the hip. These are called hip disarticulation amputations, and the prosthetics that are used for them are called hip disarticulation prosthesis, HDPs. And the problem with that is they're not advancing as much as the other prostheses. The current lower limb prostheses are insufficient in mimicking the human gait cycle, which is basically the walking cycle of a human. And that's because 1, expense, 2, the heaviness, 3, they require too much energy, and 4, they have limited movements. On the right, you can see the percentage of hip amputations that occur. And they're only about 2.2%. And over here, you can see the evolution of hip disarticulation prosthesis from 1930 to 2016. The biggest problem with hip disarticulations is that right now they're extremely heavy. As you can see in the picture right here, this person is using a passive prosthesis, and that means they have to carry around the whole weight with them wherever they go. And that means it doesn't have a power source. The power prostheses act on their own by generating forces and torques. And something we want to address is the symmetry of the limbs, the pelvic tilt, the energy consumption, and the comfort level. On the right, you can see the diagram that shows the different amputations, including the hip disarticulation, as well as the knee disarticulation. The state-of-the-art solution that we came up with was a single-axis monocentric HDP, such as the 7E7, which is pictured on the right, and the 7E5, which is very similar to that one. They have assistive extension function by elastic element, as well as what we came up with is a polycentric HDP, such as the Helix 3D or Auto 7E9, and those are more advanced. They consist of a 4-bar linkage mechanism with a hydraulic unit. You can see one of those here. This table right here shows different models, including the 7E7 and the Helix 3D, their weight and flexion angle joint mechanism category, and their max body weight in kilograms. So for the next slide, the remote center of mass mechanism. This includes a parallelogram mechanism, spherical linkages, and circular guidance arcs. The RCM mechanisms allow for a virtual hinge point called the RCM point. They can mimic hip joint constraint and pelvic socket. The links are attached in the series with each other by rotation joints, as you can see here. The next slide, I'm going to let Kathy go for the objective.
So our objective is to design hip disarticulation prosthesis with a remote center mechanism that would mimic the human gait better than existing hip disarticulation prostheses, and then to test the prototype with an amputee and compare the results with the Autobox 7E7 hip joint. Previously mentioned HDPs can assimilate the anatomical structure of a healthy leg, as the abnormal position of the hip creates different leg lengths of the prosthetic and healthy side. And so by using a RCM mechanism to make the thigh rotate around the acetabulum, the rotation center of the hip joint prosthesis can be restored back to the acetabulum. Here's an overview of the design using a remote center motion mechanism as the hip joint. T1 serves as an active translation joint for the swing phase, and T2 serves as the passive joint to provide constraints and supports for stability and stance phase. On the right is the plan for installing a battery and a linear actuator to power the prosthesis. In the parallelogram, the deflection angle of the prosthetic femur is labeled as beta. When T1 moves, it can be obtained by inverse cosine of d squared plus g squared minus e squared, all divided by 2dg. D is a variation of the translation joint T1. G is the distance between J and G, and E is the distance between P and G. The angle of the prosthesis, theta, can be obtained by pi over 2 minus beta plus mu. Mu is the constant value determined by position of point B and C. The real length of the prosthetic femur, F, can be determined by C plus P, and so the knee joint K can rotate around the hip joint H with a constant radius. This ultimately allows for symmetry between the two legs. The optimization procedure is to minimize the driving force during the swing phase and minimize the overall size of the hip disarticulation prosthesis. The genetic algorithm was used to determine the optimal placement of the pelvic socket with respect to the acetabulum, and MATLAB was used to tailor the parameters to the subject for optimal interest based on dimensional requirement obtained from the genetic algorithm. The whole hip disarticulation prosthesis consists of the 3R60 as the knee component and the IC1C10 as the foot component. We created a CAD model on SOLIDWORKS of the proposed remote center of motion hip joint. Here is a simulation of it when the linear actuator is applied at where the blue component is. This is how it should ideally work.
All right, for the evaluation also, there was a real 3D gate and motion capture system called RealGate that was used to collect the gate data. And Cipass at the M system was used to collect the measure plantar pressure. The subject walked on a treadmill at speeds of 0.5 meters per second, 1 meter per second, and 1.2 meters per second for 2 minutes. And the gait curves were averaged to 10 gait cycles. The pattern of hip angle and knee angle of the RCM HDPS resemble closely to that of the intact side, more so than the 77, as we can see in the pictures right there. Both the RCM HDP and 77 show increasing pelvic tilt compared to the intact side. The RCM HDP reduced the anterior and posterior tilt compared to the 7E7. For the walking speed of 1 meter per second, the RCM HDP improved the symmetry index of kinematic parameters of the hip and knee joints. The jumping simulation using chain model. I will continue with Hudson, I believe.
Thank you very much, Dennis. Hi, I'm Hudson, and my part of this project was the jumping simulation using KB Cheng's model, which is listed in references number 5. Most prostheses are tested for jumping, and in this project, we wanted to see how RCM mechanism would act when a person jumps with it. In order to do this, we gathered data from a normal person jumping using tracker software, and then we sent it to Python for analysis. Next slide, please. So these are the parameters gotten: the acceleration, horizontal velocity, knee joint movement, and all types of data collected with tracker up. Sending it to Python, I was able to graph the height of the knee with respect to the time frame taken, and we can see how it increases when the person is in jump phase, and then it decreases when the person comes down to the regular point. And this is also the knee joint. We can also see about the same thing, it being at about 3 degrees and then going down and then going very up when the person jumps, and then it comes down, settles down about the same joint again. Finally, I use Python, Matplotlib, and PyPlot to create a dynamic simulation. This would actually show a person from the beginning stage to the end stage and to the heightened stage, but Google Slides doesn't support dynamic simulation format. So I took the graph and pasted it here, and then the code is on the side too. Internship experience and career expectation. The Cipass internship was a very interesting one. Because the internship was online, we had a lot of meetings. I think this prepared us for our future careers. We also had to work as a team to make our goals into a successful reality. we learned a lot in this research. We learned research methods as well as time management skills and how to professionally present our findings. And these are a list of references used to help in the research. Thank you very much.